Magnetic resonance imaging, or MRI, is a non-invasive means by which radiologists in hospitals and scientists in labs are able to non-invasively image life. And it's a very widely used technique. If you've ever been to a hospital, if you've been in a car accident, or if doctors need to determine if you have internal bleeding or head traumas, MRI is an extremely powerful tool that's used to deduce information and how doctors respond appropriately. And so in this video, what I'm going to do is cover how, in practice, these MRI machines are actually working, and it's all based off something we've discussed previously, which is NMR, nuclear magnetic resonance. And for PR purposes, they drop the nuclear term, but it relies on the exact same principles. And so, as we'll recall, if we had some water molecule in a solution and we applied a very strong homogeneous magnetic field B0 in one direction, some protons will spin with this magnetic field, others will spin against it. Those that spin with will be called the alpha state, and those against will be called the beta spin state. The difference in energy between these two spin states causes a difference in energy, delta E, which will allow us to determine a Larmor frequency. And so after we kind of take a Fourier transform of the raw data that we obtain from a radio frequency generator that's operating on this Larmor frequency, this is a kind of mile-high overview, we end up getting these plots where we'll find some peak at a particular frequency value, and this y-axis will have units of like electromagnetic absorption, and this is what we get out of NMR. And the point here is that this is a homogeneous magnetic field. And these are quite strong magnetic fields in practice because we need to have large differences in energy to be able to obtain plots that aren't too noisy that we can easily see. We have a water molecule present in our solution. And so when we go into a hospital room and into an MRI machine, what's going on here is in MRI, we create magnetic gradients along planes. And what essentially happens is in 2 dimensions, we are forming very strong magnetic fields, but they have different values depending on where you are along a particular dimension in space. And so to draw an example of what this might look like, let's say we had a cube of water that was somehow suspended in space along a single dimension, and the magnetic field will be applied here. And what we would find if I called this point Z equals 0, and it will have a magnetic field strength equivalent to 10,000 Gauss. And if the point up here had a value Z equals 10 centimeters in length and a magnetic field strength equivalent to 10,010 Gauss, we've created a magnetic gradient now in the Z direction, and this would be Z equals 5 centimeters. What we would find when we take a Fourier transform of our data is we would get some kind of plot that looks like this. And so at multiple frequencies, there's going to be an absorption of our electromagnetic radiation, just the radio frequency that's passing through the sample. And so based on this principle, if we extend this from the single dimension case into multiple dimension cases, what we'll find is this. So let's say now we have 2 blocks of water suspended in 3-dimensional space, and we'll be applying some magnetic field in the same direction we had previously. It now will help us to define a coordinate system. So I'll define up to be Z, right to be X, and into the page will be Y. If we apply the same technique in which we generated a magnetic gradient At z equals 0, we had 10K Gauss, and at z was equal to 10 centimeters, we had a magnetic field strength equivalent to 10,010 Gauss. What we'll find is that we're going to get multiple plots depending on what dimension we're analyzing. So in the z dimension, what we'll find is we'll get two kind of blocks, and this will be, so in two different sets of frequencies, in two ranges of frequency values, we're going to have electromagnetic absorption of our radiation, our Larmor frequencies, and in the x dimension, we will have a big single range of absorption of our EM radiation. And in the y dimension, we will have the same case where we have a lot of absorption along a particular range of frequencies. And so based off this information, we have computers run a bunch of algorithms and just stitch all this data together, and they're able to generate these three-dimensional data figures that have kind of slices of brain tissue, for instance. And this is extremely useful to doctors who are interested in determining if patients have tumors. The main thing that we're interested in is the presence of water. So water is probably one of the most common or most abundant proton sources for these kinds of spectra that we're generating. And so that's where we're getting all of our data to generate these kinds of spectra. And one of the other things to make a final note of for MRI imaging is you'll know how you essentially are in like this donut, and there's a table, and a person will be lying on this table as they go into the MRI machine. And so what's happening there is within this donut, you essentially have a magnet that's spinning around, a very powerful magnet, and we're taking many cross slices of planes. And so what that is doing is it's being used by computer algorithms to be able to stitch a better picture of what's going on in this person's head. And so if we just did this in one dimension, we would have a figure, but there wouldn't be high resolution. So our goal is to get good resolution, and we want to do it quickly. And the mechanisms by which you'll find in these hospital rooms where they've got these donuts that people go into, where we're taking multiple planes into account, not just three, provides us with additional information that allows us to make good resolution three-dimensional images of what's going on inside of living samples and people very quickly. And so I hope you guys find this useful. Let me know if you have any questions, and thanks for watching.